Hi all, welcome to part 3 on combinational circuits. See, in the previous two parts of the video lecture, we saw what is combinational circuit and how it is different from a sequential circuit, and given a logic diagram of a particular combinational circuit, how to analyze the diagram, right? How to come up with the Boolean function corresponding to it. That is what we discussed in the last part. Now let's see the design of a typical combinational circuit. So, for a particular application, how to come up with the combination circuit for it? The design part we are seeing, right? So, from the specification of the circuit, determine the required number of input and output and assign a symbol to each. So, that is the first step. What is the input and what is the output? That you have to understand clearly, right? And assign variables for them. Derive the truth table that defines the relationship between the input and output. We will see with an example. Obtain the Boolean function for each of the output as a function of the input variable, right? And draw the logic diagram and verify the correctness of the design manually or by simulation. Let's see. So we will understand the design of a combination circuit with a typical example. So this just understand the procedure clearly, and the same thing you can apply for any kind of combination circuit design, right? So that about it. So the first example we are going to see is code conversion example, right? So converting from one code, binary codes, many codes you may gone through in your first module, right? Especially in that number system topic. So given on two coding technique, how to go from one particular coding technique to a different one. So that code conversion is what we are going to see. On typical cases, BCD to Xs3 code. So hope you remember what is BCD and what is Xs3 code. So tell me what is BCD. BCD, binary coded decimal, right? So every digit we will represent with a 4-bit binary. Something like 0 is represented by 0000001. Like that, 9 will be represented with 1001. So these are all the BCD of the digits. Suppose I have a number 76. How can I represent it in BCD? First take the BCD representation of 7, and that is 0111. Then take the BCD representation of 60110. This will be the binary coded decimal representation of this number 76. So this is one way of representing a number. That's all. In computer memory maybe, or some other application. Now another similar coding technique is Xs3 code. I don't know whether you know it or not. If you don't know, understand it right now. So what is Xs3 code? So Xs3 code is also, as the name says, some 3 is extra here, right? Some 3 is extra. Means Xs3 code, right? Some 3 is extra. So how that extra 3 is added? So it's just like this. 0 is represented by 0 plus 3, something like that, and it's BCD. 0 plus 3 is 3, 3 is BCD. Similarly, 1 is represented by 1 plus 3 is 4, the BCD representation of 4, that is this, right? Etc. How you will be representing 9? 9 will be represented by just like it's not BCD actually, I am just telling like that. Xs3 code only. 9 is represented by 9 plus 3. The binary of 9 plus 3, something like that. 9 plus 3 is 12. The binary of 12 will be 1100, right? So actually, we have to represent all digits from 0 to 9. So 4 bits are needed. That is why even though for 0 and 1, 4 bits are not needed, but still we are using 4 bit by putting more significant bits at 0, because we need a standard way of representing things, right? So that is why. So every digit in the Xs3 code is represented by some 4-bit binary of its equivalent plus 3 notation, something like that. So let me ask you how to represent the same number 76 in Xs3 code. Now it will be clear. What is Xs3 code of 7? It is 7 plus 3, that is 10 in binary, that is 1010. Similarly, what is Xs3 code of 6? It is 6 plus 3, that is 9. The 9's Xs3 code. Sorry, it's not like that. This 1010 is the Xs3 code of 7. That is binary of 10. Similarly, Xs3 code of 6 will be binary of 9. That is 1001. So, see, it has, you have to be clear about it. If you still have any doubt, you can ask me maybe in our discussion. So that is my requirement. So this has to be clear for you. So I need to come up with a combination circuit, and what is the input of this circuit, that you have to be very clear. Input of this circuit is a BCD number represented by the variables A, B, C, D. This number A, B, C, D with A as a say more significant bit and D as a least significant bit is a BCD number. So a BCD number I am applying as input to the circuit. So let me call this circuit as BCD to Xs3 code converter. So that is the combination circuit I am having. Now what is output of this circuit? That is the Xs3 code. Let me denote it by W, X, Y, Z. So this W, X, Y, Z with W say as a most significant bit. So this is the MSB and here this A is a MSB, right? And this is my Xs3 code, the equivalent Xs3 code, okay? So this kind of a conversion I want to perform. Now how to do this? So given any BCD number, the circuit is going to give you its equivalent Xs3 code. For example, I am giving the BCD number, say let me give you 1, 0, 0, 0. I am randomly giving. Tell me what is 1, 0, 0, 0 in BCD. In BCD 1, 0, 0, 0 is 8, right? It's a representation of 8. Now, what is its equivalent Xs3 code? In Xs3 code, this 8 will be represented by, its equivalent Xs3 code 8 will be represented by what? Plus 3. That is 8 plus 3 is 11, 1, 0, 1, 1. That is the equivalent Xs3 code. So, that is what I need as output 1, 0, 1, 1. So when I am applying 1, 0, 0, 0, that is 8 as a input, the circuit is supposed to give me 1, 0, 1, 1. So that is my requirement. How to do this? So what you have to do is you have to find out what is this W as a function of A, B, C, D. Similarly, find out what is this X as a function of A, B, C, D. So once you do some processing over A, B, C, D and with the help of that you try to find out what is X. Similarly, what is this F as a function of A, B, C, D? And similarly, what is that Z as a function of A, B, C, D? So that is your task. Once you get it, you can implement it using the logic diagram. That is going to do what is required for you, right? Now, for that, what I am starting. So this is my starting point. I am writing all the the truth table. So in first this is the converter truth table. So what I am doing is this is my input A, B, C, D. For input I can assume values from 0 to 9. But you know, using 4 variable, how many combinations are actually possible? I can go for 6 more combinations actually. This is my 0 to 9. 10 combinations are here. Now 6 more combinations are there, like 1, 0, 1, 0 is there. Then 1, 0, 1, 1 is there. 1, 0, sorry, 1, 1, 1, 0, 0 is there. 1, 1, 0, 1 is there. 1, 1, 1, 0 is there. And one more combination is there. A space is not there, you know, all 1. Now let's see. So first you have to find, these are all the valid input, right? So as far as the BCD to Xs3 code converter circuit is concerned, the valid input are like from 0 to 9. If I am giving any input like 1, 0, 1, 0 or up to this some 6 combinations are there, right? All of them are invalid. So if an invalid input is coming, how this the truth table will behave? Hope you remember. The circuit can output some don't care, right? So corresponding to each invalid cases, it is going to output you don't cares, right? It can be anything, right? We don't care them. These cases, some 6 such combinations are there. So that about it. So those things are not represented in the truth table. Only valid inputs are shown. So corresponding to each valid input, the corresponding Xs3 code, the output is also given. So this is my input and this is my output. For 0, it is 0, 0, 1, 1. I mean plus 3. For 1, it is 0, 1, 0, 0. That is 4. Plus 3, right? Plus 3 like that. Now you can find out, you know, what is your W as a function of A, B, C, D. So this is a truth table. As a function of A, B, C, D, this is your W. So what you have to do, you have to use your K-map for simplification. So hope you remember how to draw the K-map and all. So that is something we discussed in detail in your second module, right? So you can draw the K-map for finding what is W. Just draw the K-map, 4 variable K-map, right? 4 variable K-map. And 16 cells will be coming, right? And hope you remember how to label the cells, like 0, 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12, 13, 14, 15. Now you can fill the cells by looking at the table. You can see that. So you can, it is easy for you if you call them by midterm. So this is your midterm 0, right? This is your midterm 1, midterm 2, midterm 3, midterm 4, midterm 5. You can see that from midterm 5 to midterm 9, right? I'm getting 1. So in my truth table, midterm 5, see 0, 1, 2, 3, 4, 5. Midterm 5 to midterm 9. Midterm 5 to midterm 9. 5, 6, 7, 8, 9. These things are ones. Now what about remaining midterms, like midterm 10 to etc. midterm 15, right? So all those midterms are don't cares. So that also you have to mark. Midterm 10 we don't care, 11 we don't care, 12 we don't care, 13 we don't care, 14 we don't care, 14 and 15 we don't care. So that's all. Now you know how to simplify the K-map, how to minimize, how to come up with the minimal expression. So this is one thing you can have. So what is this corresponds to? So here you have to write down the variables, right? The input variables are like ABCD. As a function of ABCD, you are trying to find out what is your W. Okay. Now this 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. And you can see that when you are moving across the columns, this C and D vanishes, and here 1 to 0, B vanishes and A remains, right? So this entire 8 element grouping corresponds to A. Now another grouping possible for me is these two ones are remaining. I can have a group like this, 4 element group, right? For this group, tell me what is the term. This 0 to 1, A vanishes and B remains B, or here 0 to 1, C vanishes and D remains D. Yeah. Now the next one is like this particular grouping, and what it corresponds to. 0 to 1, A vanishes and B plus 1, 1. Yeah, C, B plus C, like that. And now finally the whole thing, the whole expression, so all the ones are grouped, right? So W is equal to, as a function of A, B, C, D, how can you write this W? This W is A, or, sorry, I made a big mistake, sorry for that. So this is our product terms, right? This is not sum terms. That is BC and this is BD. Sorry, it's a mistake. Hope you remember this. So from the grouping corresponds to product terms, not sum terms, because if you group 0, that corresponds to sum term. Okay, so this was C, right? Yeah. D vanishes. Fine. So A is on product term, or BD is another term, or BC is another term. So this is your W. So hope the method is clear, right? So from the, as a function of A, B, C, D, I'm finding out what is the most significant bit of the Xs3 code. ABCD is my BCD, right? BCD number. So whenever I am giving some combination for this ABCD, I have to do some conversion, some processing over them, and I have to come up with the correct value for the W, most significant bit of the Xs3 code. Similarly, you can find out what is your X as a function of ABCD. Same for variable K-map you use and simplify, and what is Y and what is A. See, I'm not spending time on it. That you can do. as an exercise, right? So right now you are very much comfortable with the K-map. Just do the simplification using K-map like that. So what we obtained is our W A plus BD plus BC. See, if you want, you can go for one more level of simplification. A plus this B you can take out. C plus D. So C plus D is coming common. See, this is my W, right? This is what I got. A plus B into C plus D. In a similar way, so this is the truth table corresponds to Z. Okay, so this corresponds to Z. See how that minimization is done. Similarly, I think here there is a mistake. You just verify this was don't care. When I cross checked, this is something I taken from the textbook. You verify. Okay, so this is I remember like don't care. I was surprised why this one they are not grouping, but actually it was not there in the original truth table. Yeah. Similarly, this one, what is my y and what is my x? W I derived, right? Same way. So you are getting expression like Z you are obtaining like a D dash, Y you are getting like a CD plus C plus D the whole complement. That you can see that the sub expression in X also C plus D complement. This sub expression C plus D is coming many times. So you can use just an OR gate and you will obtain the C plus D, and that you can repeat at different points. Okay, so if you have some common sub expression, you can reuse that part of the circuit. So this is how you can finally have this diagram. This diagram drawing is very easy for you. So just understand. So first you have to understand that the inputs are like A B C D. So the four inputs are ready now, A B C D. Now with the A B C D, what are all the things I need? First the final output has to be Wx by Z. And what I know is this Z, the most significant bit, Z is nothing but the most significant bit of the BCD number, its complement. So Z is D complement, right? Z is D complement. So this D I am taking using an inverter. D complement is my Z. Now next, what is my Y? My Y is actually CD plus C plus D the whole complement. So I am taking the C and D, I am getting the CD. Then here I am getting the C plus D, right? And I am getting its complement. So or of these two will give me Y. Okay, so just do them in a systematic way like this drawing. You have to draw a very clear diagram. Don't make things complicated. Systematically you proceed, you will get. So on the left side you list all the input variable A B C D this direction, or top down and bottom up way you can write. Similarly in the right side same way, W X Y Z. Then one by one you realize that's all, right? If something is repeatedly used, so just like this you can take it over here and there. So from here I am taking this C plus D, and that C plus D is coming here, right? So here this first input is actually C plus D. Similarly, here this is this B I am taking, so here I am getting B dash like that. Now it is clear, right? The same C plus D I am applying here also. So this is also my C plus D. I think in a W X everywhere that C plus D term is coming, right? And the remaining terms also. And hope it is clear how to draw the logic diagram. So this is very important concept. So that code converter itself is given in your syllabus as a direct topic. So they can ask you conversion between any two coding technique given. So here it is BCD to Xs3 code. They can ask you say BCD to some other coding technique also. I think hope you studied this gray code also, right? So if you know this gray code, you can try this binary to gray code conversion. Similarly, gray to binary, that is a repeatedly asking question. So if time allows, I may make a video out of for it, but you can try it, right? So what is binary and what is gray code? I think in somewhere we discussed it, that reflexive code, right? Gray code. Understand what is gray code and try this. So let me give it as your homework. What was it? Do this. Binary, normal binary you take. Binary, maybe 3-bit binary or 4-bit binary. Binary to gray code converter. Why this is important? Because I saw this question many times. That is why I am asking you to try this. So binary to gray code converter. Say how many bits you want. Say you can try for 3-bit as well as 4-bit. Okay. Similarly, say 3-bit gray to binary converter. and 4 bits gray to binary converter. So 4 questions were there. 3-bit binary to gray converter, 4-bit binary to gray converter, 3-bit gray to binary, 4-bit gray to binary. So try all the 4 questions separately and you will understand a very nice property, right? So given a binary, you can quickly find out what is the corresponding gray, provided you do it in a correct way, systematic way. You should do some kind of trick in it. So that relation you try to understand, maybe we may discuss in our subsequent video. So anyway, you make an attempt, right? So like that they can ask you, maybe BCD to gray code also they can ask you, like that anything they can ask. And that time you have to be careful. In BCD and all, yeah, the thing is that don't care where to apply don't care, that you have to be careful. So now you understood where this don't care concept is being used, right? So when it comes to BCD, so 4 input 16 combinations are there, only 10 combinations are valid, remaining 6 are invalid. And when somebody is giving you one of that invalid combination, how the circuit is going to behave? It can output you 0 or 1, but you don't care. So that is the meaning. Accordingly, we are simplifying it. Whether you are getting 0 or 1, we are okay with that because the input is invalid. That is the thing, right? Yeah. Thanks for watching.